All right, so this is 4.4, part 2 for Business Cal. We're going to continue the discussion on elasticity of demand. All right, so remember, we can find that elasticity number. If it's greater than 1, demand is elastic. If it's less than 1, demand is inelastic. So economists can calculate elasticity of demand for many products, and some typical elasticities are shown in the table. So notice that for necessities, clothing, food, demand is inelastic since consumers need them even if prices rise. While for luxuries like restaurant meals, demand is elastic since consumers can cut back or find substitutes in response to price increase. All right, you've got a whole list of things here, and you see the ones that are elastic or that will change a lot are automobiles, restaurant meals, fresh fruit, and even almost with movies. It's 0.87, so we're getting close to that 1 number. Okay, but it's inelastic for like gasoline, housing, clothing. They're much closer to 0, way less than 1, because people need those no matter what. So that demand function, x equals d of p, gives the quantity x of an item that will be demanded by customers if the price is p. And in general, demand falls as prices rise. Okay, and you see this in the graph here. As the price is getting larger, the quantities that are needed is decreasing. We're going down. And the demand function is negative as shown in the graph. This is known as the law of downward sloping demand. Okay. So how do we go about calculating elasticity if all we have is the demand function? So for a demand function, d of p, the elasticity of demand is E of p equals negative p times the derivative of p, all of that divided by d of p. And again, demand is elastic if that E of p is greater than 1, and inelastic if E of p is less than 1. Okay, so the elasticity is being composed of relative rates of change, that d over p, d prime of p over d of p. It does not depend on the units of the demand function. Therefore, elasticities can be compared between different products and even different countries. Okay, so that we're multiplying that relative rate of change times negative p. Okay, so looking at example 2. It says for a bus line, they estimate the demand function for its daily commuter tickets to be d of p equals 81 minus p squared in thousands of tickets, where p is the price in dollars between $0 and $9. Sorry. We need to find the elasticity of demand when the price is $3 and also when the price is $6. So the first thing we have to do in order to find that elasticity of demand is actually find E of p. So we need to find E of p first, and that's where we're going to go. So remember, that's negative p times d prime of t over d of p. So I have my d of p function. It's 81 minus p squared. So d prime of p would be negative 2p, just negative 2p, sorry. All right. So if we plug both of these into that elasticity formula, that E of p equals negative p times negative 2p over 81 minus p squared. Simplifying this gives us 2p squared over 81 minus p squared. Once we find this, we'll be able to use it for both parts A and part B without having to find it a second time. So if we evaluate at 3, at p equal to 3, so E of 3, that's going to be 2 times 3 squared over 81 minus 3 squared. All right, that gives us 18 over 72. So we have 9 times 2 is 18, and 81 minus 9 is 72, which gives us 1/4. All right, so what that means is the elasticity is less than 1. So for demand for tickets is inelastic at a price of $3. This means that a small price change up or down from this level will cause only a slight change in demand, not a big deal. So more precisely, elasticity of 1/4 means that a 1% price change will only cause about a 1/4% change in demand. So not a lot. All right, let's look at what happens if we have a price of 6. So E of 6. Again, that's 2 times 6 squared over 81 minus 6 squared. That's going to give us 72 over 81 minus 36, which ends up giving us 8 over 5, or 1.6. Okay, so what does that mean? This elasticity is greater than 1, so demand is elastic at a price of 6, meaning that a small change in price up or down from this level will cause a relatively large change in demand. In particular, an elasticity of 1.6 means that a price change of 1% will cause about a 1.6% change in demand. So much bigger difference as $3 as opposed to $6. So if it's a smaller price to begin with and it changes just a little bit, you don't really notice. But for this ticket, if it changes at $6 a little bit either way, that's going to cause a big change. All right, so in example 2, we find that a price of $3 demand is inelastic, so demand responds only weakly to price changes. Therefore, to increase revenue, the company should raise prices, since the higher prices will drive away only a relatively small number of customers. On the other hand, at a price of $6, demand is elastic, so demand is very responsible to price changes. In this case, to increase the revenue, the company should actually lower prices, since this will attract more than enough new customers to compensate for the price decrease. All right, so that's elasticity. And using elasticity to increase revenue. In general, to increase revenue, if demand is elastic, or that E is greater than 1, you should lower prices. If demand is inelastic, that E less than 1, you should raise prices. This should be intuitively clear. In simplest terms, you should lower prices if demand will change, and raise prices if demand will not change. All right, so this statement shows why elasticity of demand is important. To any company that cuts prices in an attempt to boost revenue, or to any utility that raises prices in order to increase revenue. Elasticity shows whether the strategy will succeed or fail. The borderline case E equal to 1, called unit elasticity, is where revenue cannot be raised, in which case, which will be the case if revenue is already at its maximum. So therefore, elasticity must be unitary when revenue is maximized. All right, and that's on the next slide as well. At maximum revenue, elasticity of demand must equal 1. So we could use this fact as a basis for a new method for maximizing revenue. But instead, we will stick with our earlier and easier method of maximizing functions by finding critical numbers. All right, just giving you another way. If you know that elasticity demand and you know where that demand is equal to 1, you could find your maximized value, but it's simpler and easier to go ahead and find the derivative and use that to find critical numbers. All right, that's the end of section 4.4.